Buenos días, buenos días. Good morning.
Hey.
Buenos días, buenos días. Good morning.
Good morning.
How's everybody doing? Just playing around with this thing. So here, this was from last class, but I did it in several ways that you can sort of make it 3D. This one has the half star sort of inscribed into it. So this one has, at the points of flex, several stars, and you can see how those work in order to give this sort of its crunch. So that's one way of making a crunch, and then this was just one star, no flex. But today we're going to do something a little bit different. So for this exercise, you're going to need a pencil. You're going to need a pencil and a pen. And an eraser, which is what I don't have with me right now. Where is my eraser? All right, I'm going to skip for now on the eraser, but if you guys got it. Good news, I found it. Okay. We're going to be looking at something called a Voronoi diagram. So a Voronoi diagram has some very specific properties, and I'm going to show you a picture of a Voronoi diagram. And if you've been here before, I want you to tell me what you see in this diagram that could be explained through folding, or something that has to do with folding in it. Let me just get that picture for you. Let's see here. So should I share it on the share screen, or should I share it on the chat? Let's share it on the chat. There we go. Okay, there we go. So there's a picture of a Voronoi diagram. And so what I want you to look at is the place that it calls it the Voronoi site. Okay, so notice, so what a Voronoi diagram is that we have cells, we have points in our pattern, which could be randomly placed, and then between them is a perpendicular. All right, so right in the midpoint of these 2 points, of these green points, called the the Voronoi vertex. No, it's not the Voronoi vertex. No, because the Voronoi vertex is the white points. I guess it's the Voronoi site. Yeah. So A on that diagram has a perpendicular on it. And that perpendicular is exactly at the midpoint. So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points in that. So get your piece of paper out and mark 11 points anywhere. Could be anywhere on your thing. So these points that I'm putting in my paper are going to be my Voronoi sites. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One more, why not? Let's put it here. Okay. So once you got your points in, what you're going to do is you're going to put them on top of each other. Now this exercise will require you to sort of, you got to be a little open with the eyes. So let's say I'm going to start with these two. So I'm going to take this point and I'm going to put it on top of that point. So I got to be looking at my overlaps. So I got to be looking like through the light almost to find it. Either that or, you could mark it with something a little bit thicker than a pencil. Putting it up to the light. There you go. Make sure. And then you don't have to crease it all the way. Just crease it, like a little bit, not the whole way through. So just to, I'm going to put it in with a pencil a little bit. Not the whole way through yet, because we're going to be constructing more. So this point is already being constructed here. Now this one with this one.
We can take any 2 points, right?
It has to be not really, you just got to also mind the Voronoi circle. So mind that diagram. So you got to put the points with the neighbor. So it's like this one is going to go to this one, and this one to this one. And then this is to this one, this to this one. So every point is going to be going to its vicinity. So that's going to be the idea. So this one, this, and then this one, this one. So I'm going to really get in there. And then these lines are going to intersect. So I already have sort of a site for this thing, or a region.
All right.
So then it's going to be this one to this one, or this one to this one. What's really cool about the Voronoi diagrams, it's how good it falls into place. One starts to wonder, like, all the hidden things that are happening. I studied them very little, but I remember when I began to sort of know about them, and I saw specifically that diagram, and I noticed that perpendicular phenomenon. And through folding so much and reading about folding, I know that when you fold 2 points, like if you do a fold where 2 points connect, the fold is going to fall exactly between, and it's going to be perpendicular to the line that connects those 2 points. So it's almost as if a fold is describing a sort of a Voronoi, the Voronoi site thing. So it's funny that I've never seen anybody do this in an exercise or otherwise. But it's pretty intuitive, or at least it's part of the folds, of what a fold can do. And well, I recommend using the pen and the pencil so you can sort of allow yourself to make mistakes when tracing. But some of you guys are probably good at this. So. In my development of this exercise, I tried going several ways. I tried using cuts at the points, like actually going through the paper so it would be easier to match them, but it actually looks just dirty. So I stick to the pencil points. Also, it's cool once you have these whole lines drawn in and you erase you do the Voronoi diagram with a pen, then you erase it all with a pencil. It's cool to see how everything just sort of disappears. Because once you lose this center point, the pattern itself becomes, you sort of lose sight of what made it become. Also notice how when there's three points like this one, it'll always intersect. Intersect, intersect, intersect. Also, something good to remember is that when you have a fold that's described by 2 points touching, there's only going to be one fold that satisfies that description. So if you see that the point lands on the point like we're doing right now, you can have faith, you can trust it, and just fold it. But you gotta try for the points to be touching, and the rest of the paper needs to sort of allow that. But that's on you, like you have to make it. Oh Lord, let's see here. Mhm. This pattern is one of those things of nature. For some reason, I'm not exactly sure why, but for some reason, I'm not big into hashtags, but the one of the few I follow, like I'm actually subscribed to, is the Voronoi Diagrams. So every now and again, I'll get GIFs, I'll get animations of people doing these, because this is a very popular pattern for computer scientists. Because what they'll do is they'll make a program that can satisfy drawing these lines very quickly, and then they'll animate it. They'll make the points move around, and the points will also be describing some very specific formation. And it's cool to see points from other patterns become their Voronoi diagrams. I've done that for several of my pieces without knowing that that's what it was, and then, lo and behold.
I'm totally gonna steal this exercise.
You're gonna steal it? Yeah, it's all yours. It's one of the cooler ones because it has some very, once you know that it's, those two things, so the folds being the perpendicular between, it's like, oh duh, that's a fold. So
I mean, we look at Voronoi diagrams in my visual mathematics class, but I haven't ever had them fold it. So that's, I mean, it's obvious now.
yeah, exactly. Once you see it, you can't unsee it, right? On which class do you see this?
The visual mathematics class that I teach.
Oh, nice. Okay, so this one's the point where it gets tricky, just to see you guys. So I got this line that goes right between these two, right? So then one starts to wonder, wait a minute, like this is going all the way down. What's wrong? Well, even though that it doesn't seem that way, this one is part of this too. So I also need the one that goes right between it, and it'll connect it. So even though once you construct and try to find, if you have something that's missing, like for instance, another one that was a little counterintuitive was this one to this one. I also complemented it there. But it'll always match. Well, Sarah, maybe you can tell us something about the Voronoi diagrams that I don't know.
Oh God.
Putting you on the spot.
All I know is that you have the perpendicular bisector between all the points and their neighbors. I don't know.
But why do you think that it's so attractive to mathematics, this sort of arrangements?
I mean, it's about space, right? Like, I mean, so the smallest distance between 2 points is a straight line, right? And so this is like the optimal social distancing between individuals, if you will.
Yeah. Very COVID themed, this.
Yeah.
I love to see it happen. Like, it's so cool once you do it and then you see all the intersections. It's so cool because it'll always fit. Also, another trick that you can do is at the point, you can sort of do a fold like this almost. So you can see, right? You can sort of just put it on that point. Of course, I'm not creasing anything, but just making sure that it falls there. And then see, so when I put that point onto the point, I go from that point towards the edge. So this is what I keep flat. I'm keeping this flat, this whole line flat, and then once I get there, boom. I could use another point here just to make it more interesting.
Can you help me out here?
Excuse me?
Can you help me out here? I think I did some, I don't know why, but I don't know if you can see. This isn't matching. So this is the perpendicular between these two dots. And I don't know, there's some glitch out here.
Let me see. Can you step it back a little bit? Let's see. There, that's good. Let's see.
Yeah, this one.
Okay, now take it back a little bit. Okay, yeah, you're missing the. Okay, so on your, which one is your right hand?
This one.
Which one? Oh, that one is your right hand. Okay, so with your pencil, can you put it on the point that's at the level of your middle finger?
This one.
Yeah, that one. Okay, so you need for that one, and then the one that's in your index on your left. Yeah, that one. You need to put those two together exactly.
Okay.
But it won't connect to the point. See, it'll draw the line that intersects.
Right.
You see that?
So
Yeah, it'll do that one, but it won't go all the way. So once you do that one, now it's about the point at the bottom there, almost at the height of your ring finger. Yeah, that one. To the two we talked about. So the one, no, rather, yeah, those two. So that's that one and the other to that one.
Okay, but then what about this little triangle that I'm getting out here?
Yeah, no, because it's too far pretty much. So because it's that far, you can even see how it doesn't play into the cell sort of movement. Yeah. So yeah, also try to make it fit. Like if it doesn't fit, maybe you can shift some things around. But not really, like it almost solves itself. This exercise was discovered last year. It was discovered last year. Good fun. So I'm giving you the fresh. One more, it doesn't hurt. If your points are a little bit too far from the edges, you'll start to see that these lines are just going to go all the way down. So, you know, sometimes I just can't help myself. Also, something I like to do, which is really useful in this case, is to use the fold as a ruler. So that means as I do my fold, and then I'm going to use the edge itself, which I have lifted up, as sort of what I use to fall back against and draw a straight line. The Voronoi diagram. Now see, in my pattern, I had this intersection and I wasn't sure what was going to go down, but I gave it a shot to this one. And since it does intersect, that's a pretty big clue. Okay, so now I'm going to draw this in with pen and erase the pencil lines and the point lines. There's a point rather. So for the types of pattern I study sometimes, the quasi-patterns, the quasi-crystalline patterns, the Voronoi diagrams are also very useful in order to understand the way that the points in those patterns sort of are separated from one another. And they create very interesting Voronoi diagrams because they can exemplify the variety of connections there are. Because like, try to put this into perspective, like try to see, it's weird to say this right now, but try to put this onto something else, like onto another pattern. Make the points represent something that you know, like a bunch of squares or hexagons, and the center of those hexagons. If you do this sort of thing on it, which, you know, I'm saying it, it sounds a little bit tedious, but if you have a computer program or something that can graphically draw, go ahead and try it. But if you don't, if you want to see, you can always do the folds. It's not that hard. Like you print a pattern and then you put the points in the center, or the pattern that you have had the points at the center of the shape. You got it printed, and now you do the folds, and then you can draw the Voronoi on the other side of your print paper. So that way, on one side you can have the pattern you're studying, on the other side you can have your Voronoi diagram. Ideas. So how you guys doing? Almost done? Oh, Sarah's done. So there's this Instagram account I follow for the Islamic patterns. It's called Islam Farid. That's the name of the account. I'm not exactly sure where this guy is from, but he apparently is some sort of scholar regarding Islamic patterns. He does actually tutorials on these things, and he also uploads his analysis of some patterns to his stories mostly. And I saw one the other day. I of course screenshot his stuff, but don't tell him. And it was a very interesting one where it was the height of the hexagon combined with the square. If you've been here before, you know that I say that several times, and that's the platinum rectangle. So there are instances of patterns in the wild that combine the height of the hexagon with a square. So that was refreshing to see. I think the one he shared was in Cairo, in Egypt. In one of those minbars. Is that what they're called, minbars? Those sort of podiums that people, I think they're podiums. I mean, that's what they're used, at least in the Christian church that I'm familiar with. I was raised Catholic. I'm Mexican, so
same as a pulpit. Same as a pulpit.
Yeah, right. Thought so. Are they actually called minbars though?
Yep.
Nice. One of the more mysterious things, quote unquote mysterious, because now people are cracking those things. Actually, there's another Instagram account called Ali Reza. I think it's Ali Reza something else, but he's an architect from Iran. And he's done several really cool analysis on several Islamic patterns and whatnot. And something that he goes into, which I think is quite mysterious and interesting, are the muqarnas. Because one is tempted, to try to do them or see how they work. And I think the muqarnas, at least from a geometrical perspective, I think that just the sort of medium that they use to completely break the rules. Like put a hexagon beside a pentagon, who cares? Just do anything and then make it 3D. It's amazing. I love the muqarnas because they can just break all the rules, make anything fit. I just noticed that these things are here. Let me get that out. There we go. A nice Voronoi diagram. Some exercise to start the day, right? All right, so moving on. Well, how you guys doing? No, we'll give you 2 more minutes or 1 more minute. Gonna get a drink of water here. You guys play board games? I get together every now and again with some friends to play chess or backgammon. Good times. Friends I play with, I can beat them at backgammon, but the other friends I get together, the chess people, it's very hard to get them. They're the kind of chess people that can identify which opening you're doing, and they'll call out the name of it, like, oh yes, the reti, very interesting. Ah, the dragon variation. Something about this is just very, very interesting. Just the fact that it's just these random assortment of points and they have a nice relationship to them, and which can be brought about very nicely by folding. So I guess now what I would be thinking, at least in the terms of folding, which is now something I might have jumped the gun a little bit there with erasing these points, but see what I'm thinking now is actually folding from the corners to the point. Maybe that not right now. Maybe that's something I can look into later, but it would be interesting to see how this would look. Like just going for that point to the center there. Like actually making little regions of these.
Now you're just doing geodesics.
Yeah, right. Sort of like that. But to actually fold these, so the valleys would be the Voronoi diagram, and then these would be mountains. So maybe they could like crunch a little bit like this one is almost. Maybe. Let's see if, no, they would all be mountains. There's no convex angle. I mean, there's no point where the pattern's sort of like going inwards. It's always very tight. I don't know. I have to look into it. But if I would do it, instead of actually folding those things, I would use a tool I use for drawing points in. Where's that tool? If you don't have it, you should get one of these. I have this one. I have another one. It's way over there, so I'm not going to get it. But these are very useful. Like you can combine this with a ruler and you can just, mark your points. I think they're called drifts, or drift pins, something like that. In Spanish, they're called punzón or troquel. They're usually more called punzón than troquel, but still. Troquel is more like what's called the die. It's one of those like manufacturing processes where you have metal sheets pasted onto a wooden board, and then you would mount this wooden board onto a machine that has a beat or rhythm in which it falls onto a piece of paper or cardboard. And that would either put some creases into that cardboard or just cut away at it. So that's how they make all your cardboard boxes, all those kinds of things. You could even see that, I don't know if you guys saw the Nintendo Labo thing that Nintendo tried to come up with. It's pretty much just like an add-on to your Switch, which you would buy the thing, but you would buy like a big box with a game off it, right? And then you would get your box and you get all these sheets of cardboard, and they would have these sort of pieces that you would have to like pop out. And you pop out all these cardboard pieces, and they would also have the crease on it. Then you would fold them. And on the video game, on the Switch screen, you would get to see actually the instructions on how these are put together. And then, it's like a whole thing, right? It's like a little project for your kid or something. But yeah, so that's a die. That's what a manufacturing process called a die is. And yeah, fun stuff. That's what translates to troquel in Spanish. So yeah, but still people use it. So we're going to take another piece of paper out. Doesn't matter if yours is A4 or letter size like mine. I'm going to fold it in half like this. And then we're going to fold it like this. So that is putting one corner onto the middle line, and we're going to slide it. So I put my point on the line, and then this is going to become my slider. I'm going to be sliding my line on that, my point on that line. And when it matches to my corner here, that's my fold. So again, a very similar thing to, if you want to think in terms of the Voronoi things, it's almost as the point is here and the other one is here. So it's almost as these 2 points are matching. So therefore, between this point and this point, this fold that we just did is the perpendicular bisector, right? Fun stuff. And now we're going to use this line as a reference. So we're going to turn it over, and you're going to see the shadow of it in the back. That's one thing you can see on, you can count on, or you could just fold this onto the fold like this. So today we're going to go into uncharted waters. So if you've been here before, you might recognize the trick we're going to do, but we haven't done this one before. So I always got to keep you on your toes, right? Can't get you complacent. So what we need now, we're not going to cut away at it yet. We might need some of the stuff in this paper, but we are going to try to put more attention onto certain things. So we're going to try and put more attention onto this big triangle that we got here. This big equilateral triangle is going to be the focus for us right now. So in order to properly focus on it, we're going to fold in the lines that go between this triangle. So we're going to fold the line that goes from here outward. And now that is just simply taking this long edge and putting it on that line like so. Okay, so that's one. And now we want the line that falls on this one. You're also going to see how this one touches up here, of course.
How did you get the equilateral triangle?
That one we got by folding. Let's see here. We're taking one of these corners and we're putting it onto this middle line. So first off, we start with our rectangular piece of paper and we folded it in half like so. And we unfolded that. And then we take one corner and we put it on the line that we just folded. And you can sort of see how you can slide it. And see, notice here how this is going to change. So keep your eye on this point, on this sort of thing. So if I slide it up, you're going to see how it's getting closer, and there's going to be a point where I'm sliding it where it will actually match to my corner. And that's where I fold. When this is flat and on the line, point on the line, right? The point where that matches with that corner, that's the fold we do. Then we turn it over and we fold what's left of the line onto the fold that we just did. So you can almost imagine this is though it was a half circle. This could be the center of your circle, and this could be your three sections of the equilateral triangles that form. So that means that this could be the point of hexagon. You could see it like that if you wanted to. Okay, so now we have two when we get the third middle line. And one goes from this point, got to put it all over here. Okay, so once we have these three lines, and also the lines that describe the equilateral triangle, like so, I'm gonna fold it for the preliminary fold, the triangular preliminary fold. So what that means pretty much is that we have lines that go from the center to the vertices, and lines that go from the center to the midpoints of the edges, the apothem. People pronounce that word differently, but the apothem. How would you pronounce it?
I always say apothem.
Apothem. Apothem. Apothem. I guess one of those cases, right? I think they're both correct. So we have the center of this big triangle, and you see how because it's an odd number, the line that goes from the corner towards the center extends onto the apothem, right? So that's the thing that happens in all the odd number polygons. The line that goes from the vertex, so that's the radius, to the center, is going to extend towards the midpoint of the edge, right? So because we're doing this sort of squishy squash fold, rather than this thing is just compressing everything, it's going to change, see? It's going to go from mountain, and then it's going to change into a valley after the center. So it starts coming in mountain, hits center, changes valley. mountain, hits center, changes valley. And that will allow us to sort of contract it. So there's two ways that this can express. One is like this, where if we were to cut it away, you could actually see the kite shape there. And the other is like this, which you can see the half triangle there. Now, I prefer to use this one, the one with the kite shape for this, what we're gonna do. So we're gonna do the trisection move. So we're gonna trisect this third. So we're gonna construct a nonagon, or also called an enneagon, a 9-sided polygon. And we're gonna do this by the magic of proximity or approximation. So we're gonna use our eyes. So you gotta be sharp. You gotta be sharp in your eyes, and you just gotta be aware of what's happening on the paper.
Can you just open it up again, or
Yeah.
I've lost which? Okay. Yeah, I think.
Yeah.
Go on. Oh no, I think I've got my valleys and mountains going the opposite direction.
Oh, it's fine. If I turn it over, you're gonna see that mine also get exchanged.
Okay, yeah.
So yeah, you can always turn your paper over, and that'll instantly invert everything.
Okay.
So we're gonna sort of do this compression on the kite form. So if you do the compression for the preliminary and it looks like this, like it has your half triangles there, then it's as simple as just opening it so much, open, does a pop, and starts closing in on the other side.
So flip it over, open it up, and then squeeze it out.
On this pop. So it's here, it's closed here on this sort of half triangle shape. And then I open it, I'm opening it. And then at this point, I'm opening it so much that it starts to close in on the other side. So see, my points are connecting are beneath here, right? On the bottom. And before, they were on top, but now it's here, the connection, see? It's on, and this point is beneath.
Okay.
So I want this kite shape.
Yes, okay.
So we're gonna do the easier one first. So this is the easier one, the one without all this excess thing, the one with the smaller one. You know, it's like we're tigers, and this is the gazelle that sort of gets separated from the pack. This is the one we're gonna go get. And so we gotta keep these two lines together. So these two lines got to get together. So we match them, we can put our finger between them like so, get them, just making sure that they're together. And then we got this thing that's gonna come down. So if we folded it simply downwards, we're gonna bisect, but we want to trisect. So we want to pinch. And so what I'd like to do is I'm holding it here, you know, notice my finger or thumb here, it's staying. So I pinch and then I slide my hand down the pinch. So I'm not really creasing here. I'm just making sure that I can do whatever it is I'm gonna do and that it hits my bottom there. So that when I do this, the fold will actually go to the bottom. So that's pretty much it. So then, once that's sort of satisfied, what I wanna do is for this to go one way. And here you can see, I hope you can see, when it falls on the line. And this pinch, this top part of the pinch falls on that wall. So you can just sort of take away and give until you can match that, and making sure again that these stay together. By the way, if any of you is listening to music, please share with the rest of the group. And I mean, like, put it in the chat so everybody can tune into your vibe or whatever. There you go. Let's see here. Okay, so once you got this down, so again, so I'm gonna get this closer to the camera so you can see. So notice that what I did is I pinched it and then I came down, and this line on the top is falling on this edge. And then this edge inside is falling on the line. So this is kind of difficult, you know, it takes some getting used to. So once you have that, I have this outer flap here. You can take this to the side like this. So I hinge it from here to the other side. And if I did this correctly, this should match also with that edge. If it doesn't fit with the edge, I can just pull it. I always sort of tend to exaggerate here a little bit. So I'll keep these two together again, and I'll hinge it one way and I'll correct it, and I'll hinge it one and I'll give it. So I'll take a little bit and give a little bit. And then I actually have this hinge. So now what I really did is that I've described my trisected triangular angle here. So I can do this as a reference for the rest. So see, I'm gonna keep this folded like this and turn it over, and now this one's gonna hinge. And so what I can do now is just make it fall and make sure that it falls on the line as well.
Sorry, I missed that one. Can you just repeat that one?
Yes,
Sorry.
so what I did was I
got those, yeah.
Yeah, we got these. And now
Yeah.
with that, I turn it over, I put that face down, and now I have these two, right? This one and this one. And so now I have this one raised, and instead of repeating the move, what I'm going to do is I'm going to use the edge that I already have solved here. So this one's solved. So what I start to take it down, and I'm just making sure, again, these two need to stick together. And when it comes down, it's gonna fall on the edge. So that's what I'm looking for, that when this one falls, this one is falling on the edge. So if I put my fingers through it like this, if I slide, I should feel both layers. They should be matching. So because these lines share a center and they match like this, the angle must be the same because they are congruent and spinning around the circle. And so now what I do is I have here the other line. This could be the line of pinch. So one we already have solved, if you will. And I put that again onto the same edge. And then this one I can turn over like this. I have this final thing. So my calculations say, well, I can sort of see that I've completed these. And I go, okay, so 1, 2, 3, 4, 5, and 6. I have 6 here and 1 here. So this one's going to become 3. So I want this to be balanced. So I'm going to put in 3 on each side. So I'm going to go 1, 2, and 3 on my left hand, and 1, 2, and 3 on my right hand. So this is a space between. That's what I put on my desk here, so that it's balanced and my center doesn't get too stressed. Now, because it's an odd-sided polygon, there's going to be at one point, we can't divide it in half. So we can't have the same amount of flaps on one side than the other. But it's fine as long as they have one difference. You know, it's all right. So one side is going to have 4 and the other is going to have 5. And you can just exchange those 4 and 5. So maybe the left is 4 first, and then the right is 4, and so on and so on. But that balance helps to keep the center stress-free. We're not stress-free, rather just, not stress overwhelmed. This one, just making sure that it goes both ways. Now, there are several Islamic patterns that use the nonagon, like use the center with the nonagon, usually combined with a 12. But see, what we've done now is we created a center that's split up into 9 slices. Well, if you look at it closely, it's going to be 18 slices. But if you look at it even more closely, you're going to see that it's 9 lines of each state. So I'm going to count the mountains here. So 1 mountain, 2 mountain, 3 mountain, 4, 5, 6, 7, 8, and 9. Now I'm going to count the valleys. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 mountains and 9 valleys, and the space between them. That's my workable space. So every 2 slices I got here is going to be 1 area. So I really have workable 9s here. So now if I wanted to actually, take it to the next level, well, what I would do is, here's some interesting tidbits. This is the edge of a nonagon. It's going to go around. You can actually see how it's limited here. I actually wanted to make a bigger one, but maybe for that we would require the center of our triangle to be at the center of the paper instead of the center being sort of a little bit offset. Something to keep in mind. Maybe for next time. What is that? Oh, we already had that one. Ba-ba-ba-bum. Just looking. So I guess it wouldn't hurt just to cut away at the triangle, because it's still, we're going to cut away at here. I thought we maybe could avoid that, but next time it'll be. So I'm not going to cut away the triangle just yet, but I do want this to be all over. So, quick way of getting that. That's another good point with the Veloc move. Indeed. See the lines, because there has to be a line and 2 points of 2 lines and 2 points that fall in order to be trisecting these. So that would be interesting to figure out which lines and which points are these. So if I sort of collapse it around the edge, right? So I can focus in on which edge I want to focus on. I want to focus on this one. I have 2 mountains there coming down. So if I had an X-Acto knife, if I was, the just get it done type, I could get to see there. So if I would cut away at that line, everything that falls after is not a nonagon. So I could, just with the scissors, with some X-Acto knife, just cut away at there. And there we go. But what if we didn't have that? What if we were stuck in an island and we had nothing to do? And we had no X-Acto knives or scissors? Well, you do by folding. So all the regular polygons have this very specific characteristic where the edge is perpendicular to the apothem. Okay? So that means that this edge that I have here is perpendicular to this line, this valley line. So I can just sort of rotate my attention. I'm going to focus on that line. And so I know that this is the end of my edge. And I know that the line I'm looking for is perpendicular to this line. So what do? Well, we fold onto the line. So I'm going to fold onto the line. When the line falls on itself, the resulting fold will be a perpendicular. So I put the fold on itself like so, and I slide it until I get to hit that edge. So it's those 2 conditions. Line falls on itself, hits this vertex, this point of this mountain point with the edge, and that I fold. Now, I might be wrong, but if I remember correctly, if my memory serves me right, this should not fall on the line. It looked like it should, but it won't. I don't know about you, but for mine it doesn't. And I remember very specifically going like, that's interesting. Because if it was easy, anybody could do it, right? So again, perpendicular. You got 2 points, so this line has to fall on itself and go through those two. So I'm just keeping an eye out here on my back for the intersection. That's one way to do it.
Is that the next radial or two? So we did the first one.
Yeah.
This,
So that was the first one, right?
yeah.
So next one goes where that line that we just folded hits the mountain. And we actually have the other one because that's part of the triangle. So we have the 2 points we want to have our fold be touching. So we want the perpendicular between these 2 points. So it's almost a Voronoi for these. No, it isn't. It's just a line that connects these 2 points done by folding. So
Oh, okay.
So I'm keeping an eye out for this on this side. See, you can almost see how I can focus in. So when I put this side onto my other side like this, the back is going to start to come at me, right? I can see the back of the paper here, right? Because it's this side, and then when I fold it, now it's on this side, and I can see sort of the folds there. I can see the intersection of these. And then just make sure that this one falls on the line, and there we go. So because we're inscribing a nonagon inside of a triangle, the line of the triangle is going to be part of my nonagon. This one. Boom, 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 boom. So now we're repeating the process, and now I have another vertex. So that's another point for a perpendicular. Now don't mind anything else. All you need to care about is that this line falls on itself and that it hits through your vertices. Everything else is just vanity. There's my nonagon, right? So it would be cool if I had more space over here, because then I could use this star that actually comes out of it. So you see the star that happens with the 3 triangles happening around. So it'd be cool if we had it over here as well, but we don't. So hey, that's life. And we got to cut away at this. So we want just the nonagon. So I have one fold. I'm going to fold it the other way, and then fold it the other way, fold it the other way, fold it other way, fold it other way, and so on. This is in order to weaken the fold. Because every fold that we do, whether it be mountain or valley, is actually a different fold. At least that's my understanding of it. Not through anything I read or experience, but more through what I experience. It's almost like something, it's almost like a quantum state or something. Like it could be both. It could be anything. But it's not really. So there's one way to look at it. So it could be that the same line is being folded the other way, or it can be that a minuscule separated line is right beside it. And they look like the same, but they're actually 2 things. So which is it? I don't know. It's probably the simpler explanation, right? It's just, yeah, it's the same line. Yeah, probably. But you can miss. So there's that. So sometimes what takes the most time is to actually do the construction, like to actually either do the nonagon or do the 9-fold division, or any of those things could be the more time-consuming part of the construction. But once you got that, it's all smooth sailing after, or hopefully. Depends on your pattern, really. But see, for instance, there's no really like a lot of patterns that are inside of a nonagon. I mean, there is, of course, a rosette that we could do, but it usually happens that it's an equilateral triangle and has either 2 divisions of 9 and 2 divisions of 12 opposite each other. But now you know how to do a nonagon on an edge of a triangle, on the center of a triangle. But if you can do it on the center, you can do it on the edge. It's pretty much the same. It's like the same sort of triangular division. And so now we have a regular nonagon. And of course, we're going to do something with it. We're going to play around with the stars it has inside. We're going to nest them. Just going to wait a couple minutes for everybody to get the nonagon in hand. So meanwhile, I could talk to you guys. If you've been here before, I think there's some new faces today. So, just in case. So we're going to do several stars. So the question would be, well, what star? How do I know which star it is? So this is how I usually draw freehand the nonagon. I would do a triangle, 3 points, and then I would just put 2 points between these, sort of around an arc almost. Right, that would be the idea. So we have a 9. And so which stars do we have? So if you remember, the rule for stars is N. Oh, damn. It's way off. Get it to be less fussy. Come on. Come on, you. There we go. So it's N/K. K has to be more than 1. K has to be less than half of how many sides it has. So we have that N is 9. So we can do N2. We can do N3. And we can do N4. So there's 3 stars. Now, one of these is a compound star, this guy. This can be simplified into three triangles. I think this is the more interesting one. This is actually the one that is seen here, almost. You can see like one triangle there, two triangle there, and three triangle there, just missing some pieces down. So it would look almost like a little bit something like this. It's 1, 2, 3, 1, 2, 3, 1, 2, 3. So now that's our nanogram. So we can either, hey Richard, how's it going, man? When was this message sent? Looking at the chat here. Oh no, 2 minutes ago. Let's see how you doing. You got your
Yeah, just to say sorry I'm late. I'll
Yeah.
walk.
So did you get to see how we did the nonagon a little bit?
No, that's why I say I'll wait, so
Okay.
don't hold up other people.
Oh, here I'll do a real quick recap. So either somebody can either make another one, or I'm gonna try actually to put this at the center this time. Make a bigger one. So you have to do a triangle first, or a division of 12. No, sorry, a division of 3. So like my mind is trying to go, okay, so how do I put a triangle there at the center? It's a triangular division at the center, but apparently like my mind is not, it's not on it right now. This could be a trick. Because this triangular division and we have this line, so that point could be my center of a triangle. That's something. But no. We just stick to what we know. So first off is to get your triangle division, and we discovered that, it doesn't make any difference whether it's a triangle or the whole rectangle. So in order for simplicity's sake, this time we're actually just going to do it on a triangle. So you can cut away at this triangle. So you can extract it. And meanwhile, the people that have the nonagon, if you're satisfied with your construction, what you can do is start to do the star polygons on it. So go for the 9-3. So you're going to go for 1 point, and then you're going to go. So here's a trick. So here's a trick in case you don't know it. You can take away slices of this, like this. See that? So you can decide how many vertices are going to be exposed to you. So here, for instance, I'm going to go for 0, 1, 2, 3, right? So that way I can actually just have this be isolated, and then I can just simply lift and just fold to the corners. And then I could unfold, and then I can sort of like shift to my next point. This is sort of the trickier part, but then it could be like this one jumps over to the next side. Still have it pulled here. Now I can do the next star, right? The next line for the star pattern. So that's one way to do it. Other way to do it would be simply to have it open up like this and have it fold down. And just making sure that it hits at the edges, right? The vertices. You gotta keep an eye out also for the line that goes between. So in this case, it's a valley. So I make sure that that's one's falling in a valley, not a mountain. Because you can see it doesn't go towards the center. It doesn't touch at the center. It has a little bit. But yeah, okay, so back to the construction over here. So we're going to extract this triangle from our rectangle. That's step number 1. So once we have our bigger triangle here extracted from the rectangle, we're going to do the preliminary folds on this one, which means that we're pretty much just going to connect corner to corner like this, vertex to vertex. 1, 2. So all 3 are going to be happening. Now, if we wanted to do an Islamic pattern and actually do the things I talk about with the 2 being 9s and 1 being 12s, well, we could do it. Like we could do it from here. You just have to imagine that this would be your trisection. This would be the thing that you want to trisect. Or further, you could divide this into 9s and then sort of bounce that off of there. Ideas. But we're now focused on getting a 9 at this center. So first thing we need to do is actually get the preliminary folds in. So I need to actually fold this and then fold it the other way. And then turn that over and fold it the other way in order to get my valleys in. So it can look like this. Boom, boom. I pop it. I got my kite looking shapes. I open this up and we're going to trisect this by eye. So I keep these 2 together in order to, not get it to be so off. I pinch. I slide. I hit my base. And I take it to one side. So when I do this, I make sure that the pinch, the spine, the line that was in the top here, we can call this the spine of it, is falling on the point, on the line that we're descending towards, and then goes one way, goes the other way. And if we did this correctly, see what we're doing is pretty much sort of doing this process of identifying. So we go one way, it's like, is it the same? Yeah. Turn it over, is it the same? Yeah. So if this is the same to this, and this is the same to this, then this is the same to this. So through congruency, we've gone around, and now we can just use that as a reference. Boom, 1. Boom, I got my spine, put it one way. So this is a rather quick way of getting a nonagon in it. And this is something that you can't do with a compass and a straight edge. You can approximate it, but you can't do it as well, or as easy. One of the things, but even so, like, I'm not making a case for like, throw away your compass, forget about it, and just fold. No, it's like, this is another tool in your toolbox. You can use this and combine it with compass and straight edge, if one were so inclined. So now all these are done. Now I'm going to pop it up, and you can see how it's a triangle split into nines. So there's 9 valleys and 9 mountains here. And so now I'm going to descend, or sort of collapse in on the preliminary again. It's 1, 2, 3, 4, 1, 2, 3, 4, 5. Then I'm going to take this thing that I have here, sort of a tool that I use for cutting. It's like a little guillotine, so I can save some time here. Oh, backwards. And there we have a little nonagon. So that's cool. What's also cool is that the line that we already have in F1, that's all at the apothem. That's the 9-3 of the apothem. Isn't that cool? The line we already had with the middle. So how about this? How about we combine the 9-3 at the apothem with the 9-3 at the vertex? See how that works out for us. So in order for the 9-3 to work, you're going to see that also you can do triangle by triangle here. So there's going to be 3 of these. So when you do one, you can then just use this edge as well as a reference. So when you fall, this line is going to fall right on it. A little bit off there. And you can see a sort of shield when you do 2 of them. It's not really the usual shield. The usual shield has this be a right angle, whereas in this case it ain't. But it's interesting. It's always very interesting to see the stars, at least for me, because then you can start to see how these points of intersection can then be more points of like the nesting more stars in and trying to combine those. And it's just a lot of fun. And a lot of the row sets are actually, they have this algorithm to them. So it's like some of them are jumping between having, so it's almost just figuring out, what you're trying to figure out is at which star and at which intersection am I drawing which star. And a lot of the Islamic patterns, they would actually draw some at the apothem and some at the vertex. So whenever, when I started analyzing these patterns, that's something I would have a hard time notating, because I would have to notate not only the star, but whether it arrived at the vertex or the apothem. So for the vertices, I'll write a V. For the apothems, I'll write an A. So it's like, you know, the 9-3 at the apothem, and then we'll write it down, So 9-3A. And then there's levels of intersection. So there's several intersections to every star. So it'd be like a second intersection, a 9-4, second intersection, a 9-2 at the vertices and whatnot. And then, you know, all these different combinations that you could do with them. And some of those would actually produce what we call rosettes. But I guess as an origami person, you know, as a paper folding person, you're more looking towards finding either something about space or something about repetition. Like something you can actually crunch, something you can actually work with. So you can be channels, or, you know, this is a very satisfying thing to do. Once you get your star in, you can try to get it to sort of pop out at you. This is one of the more basic, more rudimentary things, but still one of the cooler. What's really cool about this, and something that I never, ever, ever get tired of, is that you can always find more stars for it to combine into this. So you can always draw more stars in, and the consequence of it will allow for more things to sort of come in and out of play. And you also see how, well, because of how it's looking, you know, how these are sort of coming in a little bit too aggressively. So if we wanted to, like, you know, get out, get back, either we put another star here at the intersection, or we put another one over here. So see, this is also one of the cooler things. Okay, so, but I did say we're gonna do 2 stars to this thing. So it's gonna be the apothem 9-3 and the vertice 9-3. But I want them to be opposite because I want to really, you know, make a case, or not make a case, exemplify. In Spanish, that's the word that's coming to my mind, ejemplificar. But it's not even right in Spanish. But yeah, point being that these are opposites. So I'm going to turn my paper over, and I'm going to go again for the 9-3. So 0, 1, 2, 3. Again, I'm keeping an eye out for my vertices. So keep an eye out for my vertices in this case. And you know, you can take advantage of the triangle that's going to be inside as well. It won't be as nice as the apothem triangle in that it won't match the edges like so, like before. But it will draw a triangle, so you can, you know, at least rely on that. Because once you have 2, it's easier to see the next 2, the last 2. And, you know, it'll be nice to see that there's a little triangle there drawn in the middle. And if it don't look right, then, you know, you can always course correct. Course correct. You guys see the moon yesterday? Wasn't it pretty?
It was overcast and rainy here, so I didn't see it.
No. Well, I think it's full. If it's not full, it's just about to be. So see, there usually is this thing with the combination of vertice stars and apothem stars. You can see that this intersection for me, because they're opposites, I can actually use it. See that? See how this is sort of coming in together? It's because at this point there's a flex of it. So see that a little bit better there on that side. But see, that's the sort of thing I'm talking about. There's a very, very powerful relationship between stars. All stars. I've never seen one that doesn't have one that works, that doesn't work. Between the apothem and the vertex. If you guys find one that doesn't work, I would love to look at it. But until I actually can do all of them, I can't be sure of nothing now, can I? I can't just do it 3 times and go like, well, I guess this applies for everything. You know,
We do proof by induction.
Yeah, is that what it's called? Proof by induction?
Yeah.
Interesting. What is QED?
I forget what the exact Latin is, but it means thus it is proved.
Thus it is proved. Well, that's different. No, that's like
demonstranda, something like that.
What was it?
Something like quod erat demonstranda.
Ah.
I forget exactly. It's too long since I studied maths.
You studied math?
Well, school.
Oh, I see.
So we had to write QED, but if it was constructions, we had to do QEF. Quod erat theta or something.
What's the difference there? So when you construct a proof, it's more like, you know, I haven't proved it arithmetically, but here you can see that it kind of works.
Yeah, QED is for general mathematical proofs, I think, whilst if it's more a geometrical proof where lines are, I think that's QEF, but Sarah probably knows these terms better than I do.
I don't know. I just put a little box because I'm not fancy.
Little box, like, yeah, solved kind of thing.
Little, yeah, the little square.
But I guess we have a case for the stars relating to each other really nicely. And that's not a theorem. That doesn't sound like a theorem, but hey, maybe there's one in there.
Yeah, you put, if you can, you know, put it in a way or restate it in a way, it could be solved. We could prove it by induction.
So you can start to see how, I don't know, like, I don't know how to describe it, but there are these points in the star here that actually have an intersection there at the center of them. Like these triangles here. They have the center cast through bisections. So that's what I'm talking about with the relationships, that they have these. So now, next point would be try to find some other of these, but we're not going to worry too much about it just now. What I do want to do, okay. See, with these, we can actually do a little combination of a spiral. Because we have vertices, so we have a nonagon here at the center, like the smaller nonagon inside, see that? And we have lines that go from the vertices, so I'm going to draw in the vertices with a pencil. So this is very useful information if you're into sort of like the space origami things, because they use this quite a bit, or like the idea behind it, not this design in particular, but the idea behind this. So I have my 9 vertices, right? I got my lines that describe my nonagon, like the lines that connect these vertices, which on this case, and on this side, is a mountain. And if I extend the line, well, it goes through there. Yeah, it goes all the way out. But between them, because of the line we just did, this one is actually a valley. Oh, you can't see nothing. So this one is a valley. And it's right between. So I'm going to combine these. So I'm going to choose only one side. So I'm going to keep this going as a mountain, and then this one's going to come in as a valley. Right? I'm going to do a little spiral thing. So I'm going to keep all my right side happening. So bump, bump, going out, going out. So these lines that I'm marking are the lines that I'm going to fold. And so on. So once I got, you can see the spiral thing that's happening there. So now I'm going to try to affect these. So I'm going to try to put those in. 1, 2, 3. So this will produce a very nice spiral looking thing. And well, what we can do next, for at least for this one, is we can also just pop at the vertices like thus. There's a pop there that could be happening. But again, this is just, I think right now we're still not far enough that this could actually be a thing, but it is nice to see it crunch. This is also the basis of these sorts of designs. I'm not sure what to call these, but these are more commonplace with, no, I don't know what I'm saying. No, forget that, scratch that. There's no such thing as commonplace in this case.
Are these similar to logarithmic spirals?
I'm not sure. I don't think so. Unless, see, the thing is, like, this would be the point of a flex, right? This could be the point where, boop, boop. Right, when the line's coming in, then this could be the spiral of it. So we would need to either get it more, but I don't think so. Because at this point, like, let's say that we had a bigger nonagon, or we kept this going inside, so sort of inflating, and we actually changed the angle in which this is incidenting. I don't even know what a logarithmic spiral is. You said a logarithmic one?
Yeah. The one that we use in the Tomoku Fose shell.
Mm-hmm.
Yeah, I'm not sure. I'm just guessing.
I'm not sure either, because I'm trying to think of the description of a logarithmic one, because I think that one has to do with either, I think it was the tangent line. Is a tangent line to which arc? No, what? No, there has to be an angle in which this thing is sort of. You know what? I'll look into it. I owe you that one. Now I'm curious. But can you guys pull this one off? Like with the center nonagon star and then the spiral coming out of it at the end? And usually there's enough information in these designs that you can sort of lock it in place. But apparently for this one there isn't. So I don't know why I really like this. This could be a final shape. I dare to say this could be a final shape. But if it wasn't, what I would do is I would put in my nonagon again and actually descend these at the same time. Although they will need to have a fold addition, but the idea being I'm going to try and use this as a base for another nonagon. Because now the idea is that, well, I have this nonagon extracted, so I can just repeat the process inside of this one. So inside of this nonagon, I could do again the 9-3 and 9-3 and just keep it going. And it will resolve in more pattern, because also they will match at the vertices. So it could be like a double spiral of these things. So now I'm curious to see what kind of spiral it would produce if one were to do that. Because it would produce something. Alrighty, I think it's Islamic pattern time. So we're gonna put a pin on this. We're gonna stick with this spiral for now, but you know, you are invited to keep it going, or to try and and twist it, because there is a twist also here. So I think this is yet to be completed, but this is a very satisfactory, at least, modification of it. Almost looks like one of those orange squeezers, right? If you could cast this, right, you could cast it, you could make it a little lemon orange citric squeezer. This could be a design for it. You know, if one were so inclined on industrial design, this could be a source of inspiration. I like it. It's cool. It's simple. It's happening. Again, we're going to put a pin on this because we're going to try to build up to it in another class, actually doing that pattern with the 9 and the 12. So we're going to build up to it. So we're going to put this aside for now. We're going to take out another piece of paper. Now, for this exercise that I want to do, I want to actually look at overlaps. So we're going to do a very quote unquote simple pattern, but the idea is that we want to do it on a segment which is sort of contracted in. So we want to do a pattern that is sort of a result of consequence, a result of something just like, instead of doing what we usually do, is just like trying to find the folds on each corner. We're going to try to find more folds of the pattern. We're going to try to see what would happen if we could actually pretend that the paper is not a 3D object, as though it were zero thickness. So we're going to keep it simple, but we are going to spice it up a bit. So we're going to need a square. And you will use the diagonal, so don't you worry about that. Cut away at this square. Now, again, I usually use print paper for all my needs, but the idea is something that I personally haven't developed much, but it is something I do suggest because I do believe it's the better way. It's to use the print paper as a sort of draft paper. It's to try to use it to just put your ideas onto paper, and then once you have done that, you can then translate the pattern that you like onto a fancier paper, a nicer paper. And usually the result is much more pleasing, and you can actually frame it, you can actually do something that's nice with it, and also try to combine the graphic of the design, like to a graphic design, and apply it to the origami design. So that kind of thing is always fun. But we're just worried now about folding something, and then it's up to you to see how you sort of take advantage of this. So we're going to fold the other diagonal as well. And we are going to do a fourfold. It's going to be at the corners, but we don't mind. We can do the preliminary fold as well. So again, so this is an even polygon, right? So it goes that the line that crosses each of these vertices is the same state. So a vertex is opposite a vertex. So there's this relationship that's very interesting between the circle and the hexagon, and the circle and the square. So both the square and the hexagon have a very intimate relationship to the circle. And the circle has a very intimate relationship to the world and reality and life and Islamic patterns and God and whatever. God and whatever. But so the sum of the internal angles of a square is the same as a circle. So we have 2 pi inside of the square. And the hexagon is naturally inscribed into the circle. So it's those two things that make the hexagon and the square sort of like cousins or brothers or something like that. But both of them have a very intimate relationship to the circle, which is worth noting, I feel. So again, just putting my preliminary folds in. Line to go, valley, mountain, valley, mountain. Now we're going to fold corner to the center. I'm doing the same fold. So if my diagonal here is a valley, this line I'm going to do is also a valley. Unfold it. We're going to turn it over. And now we're going to do a fold that goes between these. So we're almost folding like the apothem to the center. So center of the edge to the center, center of the edge to the center. Again, if you're familiar with origami, this is going to be sticking out like a sore thumb. Because this is the base for either the pajarita or, what else was it? Oh yeah, the fortune teller.
Windmill.
Yeah, the
as
windmill,
well.
the fortune teller. The whole lot of things in this base.
I think it's also the first part of the spinner, the usual spinner.
Yeah. So it's a lot of fun. So what we're going to do is we're going to try to imagine what's happening here. So we're just going to have to identify several things. So for instance, we have the center. We could imagine, we could put in different things at different places. So it's just a matter of where we're going to locate the pattern that we're going to work with. So is our pattern going to be centered at the corners, or is our pattern going to be centered at the center here? So what's it going to be? So I suggest that we do it at these points. So at these 4 points is where we're going to find our star pattern. That's the general idea. So what we're going to do is we're going to bisect all of these. So bisect this is going to be an 8-fold pattern, right? But one is tempted to think that we could actually even do this for a 12-fold, which can also be found inside of a square. So now we need to do it on the other side as well. But for this case, we're just going to sort of put it on. There's going to be too much stuff happening, but we just want the fold that arrives there. That's all we need. We don't need to go all the way. We just need there. You know what? I take it back. I think it's better that we unfold these that we have, turn it over, and actually do the whole thing. I think that might be better. So I unfolded these little guys here that I have. I unfolded them, I took it back, and then boom. So we're pretty much just extending all the way. I think this is the better way. So now let's try and unfold this, see what we got. So we have some pieces, don't we? Wait, I could do a little bit more there. I think I missed one. Yep. So now we open the thing and we will, what sticks out to you? What is the thing that you can see the most? For me, it's these shapes. What about you? What do you see? Now, because we don't have the eightfold at the center, rather at the corners here, so we could actually also look at this in several ways. This is very interesting. But I feel we are missing some folds, of course, but now it's about finding how to get those. Let's see here. So if I return, now that I saw what's happening and I can see sort of what's missing. So what is missing? Well, I'm missing the eightfoldness. I have a fourfoldness, so it's going four ways, but I'm missing one way. So I can have it here and I can see sort of the shape I'm getting over here. You can see even my star at the center here. And so I want this to be over here, the same sort of sequence. See, now I'm looking for where it could it be. Yes, indeed. So it's the corner to the intersection. So you can even see how these lines can sort of help us understand what's happening. So if we kept this line going, we could actually mark there an 8-3 star inside. We have a little square here. And actually, in order to get lines, we actually need to fold these. So not even really extending much. I'm just putting it on the line and then I'm just sort of folding those valleys into it. No, rather what it is for those 4 to be folded in and then refold, or just fold onto that overlap, the line from this star, pretty much. So when you just fold your star, you just gotta make sure that it goes through the overlap. You can even see how this one will hit an interesting intersection there. You know, one apparently as well as one, we're so inclined we could actually collapse this, but it's a little bit too thick for my taste. But hey, it's there. Now we actually have the 4-foldness, the 8-foldness, sorry. Fascinating. I added another line another fold, and it gave me a whole nother pattern. But for right now, I'm just gonna worry about the one we were building. What's cool is you even get to see the cross happening here. So you get to see even like the little square where this cross is inside of. You know, a very typical pattern, but still, it's a powerful one. And what we've seen before, how this pattern could be further explained, further developed. So we can look at it again, though. No harm done. But we gotta keep it fresh. So this is more like the magic trick method, you know, just do a little couple folds, you overlap, and then you do something else, and boom, all of a sudden you can unfold it, and there's your pattern. So what this suggests as well is that if we actually had some scissors or an X-Acto knife, we could actually cut away at where the pattern is, right? Everybody doing okay with this one? I'm gonna take the silence as a yes. I'm gonna take it as everybody's having so much fun that they can't even answer.
I think I didn't do a couple of the lines that you did.
Which one did you do?
I don't know. I don't have the little houses.
On these?
Yeah.
Oh, these. See here. So the little house lines are, well, they are these lines actually. They are the 8-fold lines. So you gotta do these one way.
Okay, I did those.
Yeah, and then on the other side as well, you did those?
Yeah.
Okay, then it's point to the intersection there.
I did that.
Yeah. And now it's doing the overlap.
Okay, maybe that's what I was missing.
Hopefully.
Just that extra little crease on that part.
Yeah. Well, that completes the house, the torso shape. Well, mine is sort of gives it to me incomplete, but I can sort of infer. Okay, like I have the line. It's just a little like it's not here. So this point I'm drawing my line in, it's not the line ain't there because of the way it's sort of overlapped. But it's just this segment where it isn't at.
Okay.
But the rest of the line is there. So what's interesting about this is that it suggests that if we had a paper with no thickness, and we found the fold divisions in order to draw these in, we could actually just go for those and then just find where these folds are located. And that's how we could do Islamic patterns, by this sort of process. But for right now, I guess it's just an idea. Or rather, it's more about trying to find which patterns could actually be done with what we got, right? Because we can only work with so much of reality. So yeah, try to keep an eye out for any other possible relationship that you might find. And again, also note how there isn't a part of the fold at one point. So if you're drawing it in, you can just sort of extend it towards there, or you could just fold that extension. So by dividing where we divided, we put centers over here. So these 4 points, we have centers of divisions, of eightfold divisions. And just by virtue of them, this pattern comes about. So we don't even need the eightfold division here at the center. Rather, we just need the eightfold divisions at these 4 points. So it's almost as if these were our circles. So this is our tile almost. But it's not just that. So it requires a little bit outward, a little bit further than what it has in order to fully express the potential. But you can see how this is mirrored. So these squares over here are getting mirrored over here, except that like they aren't, right? I mean, the shape is the same, but we are decorating it differently. And now the way we're decorating actually allows for this to be a half star. So if we combine it with one on the other side, we can actually get then a different sort of arrangement. Right? So if I did this, well, if it was actually complete on this side, you could see a different arrangement. See? So also suggesting further possibilities. And I would insist on the cutting, like on the folding and then cutting away at certain points so you can draw the pattern in and then refold it and see where the lines are. And you can then cut between them. So be careful with the cuts, because usually either they will completely separate the paper from itself, or they will rock your world. So keep an eye out. What's cool is that we also get to see these octagon shapes side by side. So I feel that if we extended these octagons like so, we went all the way, we see that it's almost as if this could be an octagram at the center. So it's these interacting octagrams that we're sort of matching here, but they're just really a consequence of this division. But it's, again, a very natural part of the sequence. And this also falls really nicely into the idea that they are folds, right? We call these patterns by their fold. Now what I'm looking at is seeing an arrangement, looking for an arrangement that will allow for this octagon to actually close its ring. But if I do that, well, either these two torso shapes overlap and I don't want that, or I'm missing something. And there's always usually like a square that combines these two, but I don't favor it that much, that shape.
I don't know why I don't have those torso shapes. I don't know if I'm missing something.
Which ones?
The torso shape, the one that's on your index and the thumb. You just moved your thumb.
Here?
Yeah, that one.
You don't have these shapes?
I don't know if I'm missing something. I don't know.
Okay, so let me just retrace it a little bit here. So again, I want to keep an eye out for this line, okay? So when I fold this, try to keep an eye on it. Don't on mine, so see where it falls. So it's here and it's here. So it's this.
Yeah, I
It's,
think I missed.
yeah, so it's almost as if you fold this into the base of the windmill base, and then you fold the eightfoldness.
Mm-hmm.
You go onto the diagonal. Did that clear it up for you? Did you get it?
Yeah. Mm.
There's something about this exercise that really just screams to me potential. Because just of the way that we could sort of put the idea into something else is what it's most enticing to me. Just the possibility of this being a way we can sort of shortcut in order to get a proper Islamic pattern is what's very, very interesting to me. Also, how to combine these into origami figures is also quite fun. For instance, one could squash these squares away. Fun stuff. Did that give you the house shape? Did you get it? I hope so. Also, once you put your fold in, try to refold and actually like keep an eye out for the line. See how if you can trace the way it's sort of coming in.
I like how syncing with squares emphasizes that central octagon.
Yeah, isn't it cool? And like try to refold the star into it. You see how easy it is.
Yeah.
It's so natural. And also what you can do is now you can think of like, well, I got an octagon. I could do to it what I do to an octagon.
Yeah.
And so you could like try to put in that octagon like the 8-3, and you could like put it in. It'll overlap over everything else and see what that does. It's not obvious. That's what's cool about the folds. Like they're so complicated. They're so beyond imagination. You just got to do it to see what it's going to do. So you might not see these full houses. Like I insist, this line is missing, but you do get to see the cross. The cross should be there. And again, the square, you don't get to see it complete. There's a line there that's missing on the square, but you get the cross. And we care about the cross. So again, if you put the cross over here, I guess that makes it, but no. I mean, no, I'd rather have the octagram. Anyway, so once I have it on both sides, I can actually see what I was talking to you guys about. How can I fold it and sort of see how it will complete. You know, it's interesting because I feel that perhaps to have it folded like this or like any other way could serve as a better tile than the full square. At least that's what I'm sort of intuiting here. But again, the possibilities is what this is about. There might be something that we could add to this, I feel. But how are we doing on time? 2:12. All right, I think it's modular time. All right, so new piece of paper. So we're gonna put that Islamic pattern aside for now. So far we've done the nonagon, a little spiral on it. We've done the Voronoi diagram, and now we did an Islamic pattern by overlap. And now we're gonna do two different modulars. One is super simple, but incredibly effective. And the other is super simple, but it's not that effective. And they're very different. One is sort of like the Sonobe analog, and the other is just something that's quite limited to making a cuboctahedron. So that's if we were to call it in those Schlafly symbols that we use, it would be the 3-4-3-4. So what we need is many squares. So it's not good enough for me to show you on the big square. I am going to show you in the big square, but what I want to do first is construct with you the squares that we're going to use for our pattern. So the question is going to be, how many squares are we going to get out of the big square? Now, the easier answer is, well, just cut it in half. Just go for halves and then get that out. But we want to spice things up a little bit. We don't want it to be so simple. Well, yeah, we do, but a little taste to it, right? So we're not going to go for halves. We're not going to go for halves. We're going to go for sixths. So we're going to split this into a 6x6. No, a 3x3. So we want 9 squares. Again, keeping with the theme of 9. So if you've been here before, you've probably seen this trick. This is the Hara theorem. Now, I'm not sure, I can't remember the Hara theorem, but I remember certain tricks of it. One of the tricks of it is that I can fold my square piece of paper in half like this, but I don't really need to fold the whole thing in half. I just need a top line. So I can just fold that in half, and then I just fold that line, that point on the top there. I'm going to turn it over because it's easier for me to see the point if it's a mountain. So that's just me. And then I'm going to take opposite corner and land it over there. So whoppa, and then I land it. This one I can fold, but what I really want, it's not a Spice Girl reference, is where this line hits the edge over there. So what I mean by that is that line over there is hitting the top point, and then there's some excess paper that's coming out of here. I care about this point. So, I'm not going to care too much about the line. It's not going to distract me from the rest of my construction. But what I really want is that point that hits there. So on that point, I'm going to turn my paper over. You're going to see now that that's where the excess is. I'm going to land this corner onto there. So whoop, boom, that's it. Bum, bum. And I fold that. So where the corner hits that excess, that's where I'm folding. Now, we did this correctly, and we unfold that fold that was there. And then we fold this onto the other points. So cut this rectangle in half. If we did this correctly, we should find that it falls on the other one on the other side. And therefore, these are all the same by congruency. Because this is the same as this, and this is the same as that. Oh, got fussy. Come on, you. There we go. So we got 3 columns, and that's called the Hara theorem. The Hara theorem is sort of finding a division on the edge of a square and then matching a corner towards it. So that's, I'm going to rotate a lot. I got lost with that point. Boom, boom, over there. Excess over there. Now, I recommend that you go into the Wikipedia page of this. The Wikipedia page is like the mathematics of paper folding. And you will see a segment on the Haga theorem. And this is usually like the most popular one. But as a fun fact, you know, if we actually got, instead of the half, the quarter, and we repeated this, we would get a fifth. But it depends on which corner you use, by the way, when you change it into that, because the half, it's going to be the same. But if you have a fourth and you shoot this one up there, it's going to give you a different reference. We're gonna put a pin on that for now. And we have a diagonal line. So then the question is, all right, okay, that's good. I can have my columns, but what about my rows, right? So because this is a square and we have a diagonal line, we actually have the points where the square is complete, right? We have the intersections with the diagonal. So therefore, just take this, match it up to there, like so. You can even see the little square popping up at you. So that's one, and turn it over. And that's two. Now, at first I was suggesting like, let's cut these in half, but no. Let's just cut these 9 squares. So these are going to be the ones we're going to use for our pattern, for our modular. So what's cool about having smaller size paper for a modular is like when you're done, you can actually hold it in one hand, like in a little universe, like in the palm of your hand. Instead of, well, not that it's wrong, but like the last modulars we've done, it's been on full squares of paper. So it usually ends up being like this huge thing. So again, I'm just folding every which way. By the way, this is very powerful. Like this 3x3, if one were so inclined and like actually get to fold this, it's quite something. We're gonna put a pin on that for now though. Now, the more you fold, the easier it's going to become to see the folds, to see the relationships the folds are in. And eventually, the more you do it, it'll become a sort of second nature. And that would be the ultimate. Like if you can get to where you're not thinking about what you're doing, rather you're just sort of reacting to it, or you're letting it happen almost. That's the goal. That's where you want to be at. But in order to get to that, you have to go through what you're trying to avoid. So if we're trying to avoid thinking, we got to go through the valley of thinking, right? We got to go through thinking first. And then after a lot of thinking, we won't need to think anymore. It'll be written in our code. But so there are certain hiccups with following instructions. One of those is that following the diagrams will make you think that that's the only way of arriving at that result. And so experience has taught me that there is no such thing as just one way to do things. There are many ways to do everything. Now, a lot of the origami designs for the diagrams are based on having a way to get there that's fun and entertaining, and cool. And that's a lot of the thing. Like they're not really selling or like the final piece, which they are kind of, but they're also saying the process, how fun it is to get there. So a lot of the steps sometimes are a little redundant, but they're part of making it fun. So that's interesting as well to take into account. So it's not just about the nuts and bolts of results, but rather the process, right? How fun it is to actually get there. All right, so we have the 9 squares. So that's a nice little collection we've got. So for one of these, we're going to need 6 pieces. We're going to complete one, and the other we're actually going to need a lot more. So we're going to do both of them. So this is going to strike you as familiar. So I'm going to fold, not the preliminary fold. I just want my center right now. So I just fold 2 diagonals on it. So 1 diagonal, 2 diagonal. Some of your squares will have diagonals, some won't. But it's fine. So again, corner to the center. So if my diagonals are valleys, I'm going to fold these in valleys as well. Keep keep the system going. Not the system, but just keep it tidy. Now, looking at this, what part of the paper is this point? None of ours, of course, is a vertex of a square, but what part of the paper is this point? So if we unfold it, lo and behold, that is the midpoint of the edge. So if the next step is midpoint to the edge and we have it like this, well, couldn't we just turn it over and fold again, corner to the center in an overlap? Well, if you've come into origami at all, you probably know this one, right? I'm gonna put in the fortune teller mode just because out of principle, but this is not it. This is not the module. Again, just out of principle, I gotta do it. But I'm gonna undo it. And see now what's cool about that sort of configuration is that it gives us these pressure points. See these points there in the middle, which we already did on the design before. Like that, so same thing as before. Only that this time, we're gonna call this done. This is the module, this is the cell, this is all. So we've done this, we put it aside, we do more. We need to do 6 of these. So this isn't hard, right? Pretty easy. So I'm gonna do 3 just to show you. And then we're gonna move on to the next one, but you're gonna have to finish that one on your own. Well, you're all doing it on your own. I mean, I'm kind of used to saying it like that because, see, before this COVID stuff, I used to teach origami, and it was a lot of fun, and I enjoyed it. And it was going out with the people and talking with them and going about, and I had a whiteboard and I had my markers that I took with me. It was great. But then, you know, I can't be around people no more. But when it was the classes, I had this habit, which was something that I actually had I had a hard time not falling for it. But if a person was like looking especially sad and broken that they couldn't do it on their own, I would do it for them. I would actually go up to them and I would do it for them, take the paper away from their hands, not like that, but you know, almost, and sort of get them to that point. They're like, all right, there you go, you know, hand it back to them. And the more I thought about it, the more I realized that that way of teaching them actually robbed them of the experience of doing it on their own. So the next time they wanted to try it out, if ever, and I wasn't around, what were they going to do? You know, I couldn't be there always. So it's something that I caught myself doing, and I stopped doing it after a while. But it's difficult for some people to sort of dare make mistakes, or just, yeah, that's a big part of it. It's hard to swallow failure because it's not really failure, it's just paper folding, right? But you know that phrase, making a mountain out of an anthill, something like that? A molehill? Mountain out of a molehill, something like that? So yeah, the idea is that it's a small thing, but you can make it out to be like this huge when it really isn't. So this is how this is going to combine, just so you guys can see. So we have these, which you can imagine to sort of swoop in. They're going to represent one of these 4. So in order to keep it tidy, keep it nice, we're going to do 2 on each. So the next one is going to come in here, and this one's going to be between, right? So for this one, these are going to come onto here. So we got to keep it 2 and 2. So if this is going to make a square, right? So we're also like making a cube almost. And we got that these represent the square faces of a cuboctahedron. Well, how many squares does a cuboctahedron have? And the answer to that is 6. So the way I look at it, okay, so there's the Platonic solids, right? And then there's the Archimedean solids. So the Platonic solids have the same shape to form the structure of them. And the Archimedean solids have several shapes, so several polygons, and make convex polyhedra. That means, I don't know what it means exactly, but I know that it can mean that the vertices of the solid can be mapped onto a sphere. And I guess retain symmetry or something like that. Maybe it's a little bit more complicated, but in essence, right? And yeah, so there's very specific maps to these. And when you look at them closely, you see that the Archimedean solids, although that they combine the shapes, usually have the same amount of shapes as their Platonic solids. So I mean that, okay, so take the cuboctahedron. Now look at the name, cuboctahedron, and you're going to see that it's made up of triangles and squares. So the octahedron, and the word is a clue. So what is the octahedron? The octahedron is 8 triangles. So we know that with 8 triangles, we can make a sort of that shape. And a cube is 6. So it's like we're taking both of the possibilities of a closure and just combining them. Combining the 6 squares you need to close with the 8 triangles you need to close. And they have this little nice relationship, the cube and the octahedron, right? So it's 6 and 8, so that's 12. So it would be the, wait, no, is that right? The cuboctahedron is a dodecahedron? 8 and 6, no, that's 14. Look at me with my arithmetic. So it would be a tetradecahedron. But they call it a cuboctahedron for convenient purposes. They do that several times. So like take for instance the icosahedron, right? That's another big clue in the name. Icosa, that's 20. Dodecahedron, we know that that's 12. Those are the pentagons. And effectively, it's 20 triangles and 12 pentagons. But again, those two are related to they have a Platonic solid counterpart that they're sort of like being integrated into. I don't know, can you imagine people like going on these like geometrical adventures before computers, just like sitting down at a desk, writing things down, making prototypes out of paper, going like, are you guys seeing this? Like, how crazy can you get? So yeah, this is the intention of this thing. And what's cool about it is that actually, like once you get it into position, which is kind of hard to close, but once you get it to close and you drop it, it will like break into the pieces again. So that's cool. You can put like a little note inside and then throw it at somebody, and the note will come out. They will know what hit them. Yeah, pardon the pun. So we need 3 more of these in order to get it to close in the cuboctahedron. But now I'm going to take a little detour because of time. I'm going to show you this other modular because 1 is not enough. This one's called the Bascetta unit. This is actually the true Bascetta unit. This is like the one, the biggie. He came up with a lot, like Paolo Bascetta just came up with a lot of modular designs. As far as I know, he's come up with several that are fascinating. Interestingly enough, if you go to this guy's website, he's more about other type of art now. But there was a time where this guy was just like on top of his game, making modulars. So he's a great origami paper artist. So for this Bascetta unit, one of those, he needs to name better these things though, is that we have a diagonal of a square. Diagonal, we unfold, we fold one edge onto it, and we fold the opposite edge onto it as well. So we can have this little weird looking shape there. This parallelogram. And now with this, we overlap and we fold one to the other, but we just want the center. We don't want much. We just want the center there. Just want the point that's at the center. And now this is the part that's just genius. This is just next level. Next level simple, next simple genius. All we need to do is we're going to do a slider. So we raise this edge onto it, but we want it to come from the corner. So we want this to be spiky. So now we're actually, this is called a pivot. I call it a pivot. When we have a point that we're sort of around, so we're coming out from this corner, and we're going to pivot it until the edge matches the center point. So there's no obvious relationship other than that center point matching the edge. So the edge touches that center point and comes out from the corner. And because it's the center, the other one is just going to have to match it. And then we can hide these underneath the layer. And then we have a slit. We fold that up. And then corner to the down there. And this is the Bascetta unit. Pretty simple, pretty powerful. Now what's cool about this one, so we gotta do a little bit more of them. So when you do more, you actually have to be sure that these match. So you gotta remember, okay, so for me it was diagonal from bottom left to top right, and then bottom right corner to the diagonal. So top right corner, top left, top right to the diagonal, top left to the diagonal. No, bottom right, top left. And then my center. And then my edge that matches up to it and pivots to my corner. That's one. This is a great module for lamps. So if you're into making paper lamps, this is right up your alley.
Is this similar to the traditional Japanese kusudama?
Is this what?
Is this similar to the traditional Japanese kusudama?
Well, kusudama means just modular origami. So I think you might be talking about the sonobe. The sonobe being like so stop me if you recognize it.
Okay.
Have you ever done this one before?
I think I mean the modules, the pieces look similar.
Yeah. See, this is starting to look like it.
I think I'm missing something there. What did you do after so I did the pivot?
Sorry, I went on a tangent, but this is the sonobe. So this is, what's funny is that this is not traditional, but modern. Like this was invented in the 60s or discovered in the 60s by a dude named Sonobe. And the true power of this was not really established until the 80s. It was 20 years after it was published in the magazine that this came into like really more powerful use. Okay, so for this one, for the Bascetta unit, it's diagonal. And well, personally, I'm going for this, but what you just need to know is that your pieces need to be congruent. So your pieces need to fall into each other like this. So in order to guarantee this, we're just keeping in mind, so I'm going like this and going like that. And now what I do is corner to the top like so. And I'm just getting this reference. I'm gonna draw this in with a pencil just because I want to show you. So notice that that's my center point. And now notice how it's, so I'm coming in spiky here, and then I'm pivoting until the edge touches exactly with that line. So you're gonna also notice how this is not gonna be complete, so it won't fall on the edge, but that's okay because once we do that, we're going to tuck it behind the layer underneath. So it won't even be there. Yeah, this is one of those things that also you can't unsee. So once you do this design, it's like, ah, yeah, that's obvious. That's so easy. But, you know, he was the one that saw it. And so with 3, we can do the basic design, but I'm going to show you why this is not as stable. It is pretty effective, but it's not as stable as a Sonobe. So once we put 3 together, the big standout is that it's actually hollow. There's a hole there on the top of the pyramid. So that's why it's so cool for labs, because the light can actually escape. It's not completely tied up. So again, very cool to have a natural hole in your shape. So the more pieces you do, the bigger it becomes. And again, we're having, so when you combine these shapes, all you need to take into account, well, there's several things. One of the big things you need to take into account is that you're using triangular pyramids. So when constructing, you only care about the base. So that's what you keep in mind. So I'm using triangular pyramids. So you look at the list of solids and you go, okay, so what can I do with a triangle? And then you're gonna start to thinking several things like, all right, so what else could I do? Or how can I make this be a 5? Or how can I make this be a 4? And there are actually ways that one can go about that business. So I guess I'm gonna finish this one up. So the thing I like about following diagrams in the origami world, so following the instructions of an origami design, is to try perhaps to go into the mind of the person who is actually discovering it. Because when you're doing it, okay, so you do it one time, you're following the instructions and you're like, all right, so I can see where he's going and I can see, okay, boom, boom, boom. You spend like an hour on it or whatever, and then all of a sudden, like, it's a dolphin. All right, so cool. Then you're done with the dolphin and you come back and you start over. But now you know where you're going and you know where you're going, you know where you're going to cross through. So the second time around, you start to, you look closer. What are the things that this guy is noticing? What could be what he or she was taking into account in order to construct the shape? And so going into the mind of another person through the instructions can help you, perhaps, in your own designs or your own time, sort of use that sort of insight for your own purposes, for your own nefarious deeds. Not that I'm implying anything about it. But yeah, that's something that I like about folding Islamic origami patterns from instructions. The insight into another person's ideas. And it's something I got into it late in the game. Like, I've been folding for years, and only did I start actually to see the diagrams when I started teaching kids, and the kids were like, can we do a fox? Or they asked me, like, do you know how to do the airplane? I was like, no, I don't do airplanes. But I had to learn how to do airplanes, or otherwise, not a very good origami teacher. Besides, I thought, like, how hard it is to just like look for some diagrams for the kids. Come on. Yeah, but I used to be a little more proud. Not that I'm not anymore, but I used to be a little bit more. And I was like, no, I only fold my stuff. I only need my ideas. But now that I do it, I'm like, oh no, there's great worth in actually going like sharing mind, like, you know, maybe we aren't all knowing, all capable. We need help every now and again.
Diagrams seem to be almost a dying breed now with all these YouTube videos.
Yeah.
It's rather sad, I think.
Yeah, I agree. Although I don't think the YouTube videos count for a publication. So for instance, I think that you can actually patent your design. So there are several designs that, at least in Japan, I know they still do this more. Like if somebody comes up with an original design, they won't do a YouTube video about it. They'll publish it in a magazine because they have more origami magazines and that kind of stuff over there. So also that's more open, and then it becomes like, you know, somebody does it and they ask how you did it, where you got it, and they can actually point to a publication. And then, well, it used to be that you couldn't or you shouldn't teach or show how to do designs that you didn't design. But with the YouTube videos now, it's just so hard to keep track because some dude in Venezuela is going to do it. And you're over there in Japan with your designs. Like, what are you going to do? How are you going to find them anyway? I don't know if that makes sense.
Lots of people who publish YouTube videos who never give any credit to the original designer.
Yeah.
Occasionally, if I see one and I recognize the design, I'll put a comment in that this is original model was by so and so, and the diagrams can be found in this book.
You know, it reminds me of this thing of, I forget the name of it, but it says that if you want the right answer, just publish on the internet the wrong answer. Somebody's gonna chime in going like, excuse me, that's incorrect, or whatever. So that's, yeah. So if you want the right answer, just publish a purposely wrong answer and somebody's gonna come along and correct you. There's several like of these like internet laws. That's one of them. The other one is that if you let an internet conversation go on long enough, it's eventually somebody's gonna talk about Hitler. I forget the name of that, but it's like a law of the internet. It's weird that people just have this fascination for like eventually just the conversation just goes like, well, I don't know, it's a Nazism. Never really went away. And I've done that. Like I actually have purposely put in, not the Hitler thing, but like the purposely put in wrong information in order for somebody to try and correct me. And it usually has worked, not on Instagram so much. On Instagram, every now and again, it will happen that I will discover a model and I look at it and I'm thinking, nah, there's no way I could have done this. Like I can't be the first one. So I actually will put in a little doubt in there in my comment or the description going like, well, I discovered it, but I'm sure that I can't be the first. And usually somebody will chime in like, oh yeah, this is whatever fulanito de tals, you know, stuff. John Doe from the so-and-so, etc. It's like, oh, gee, thanks. And then, well, if they have an Instagram handle, I'll put it on there after the fact. For some reason, it's like, I'm going to tag you even though that I didn't actually use your work, but hey, I guess it's yours, so here you go. But what's weird is they actually like go, oh, thank you. So it's weird how people can actually like feel they have ownership over ideas. Hey, that's part of life. That's the American way. I saw this documentary about, I forget the name of the city, but it's a city in China that has this incredible ecosystem for electronical development, whether it be software or just like things, just like electrical things, like locators for your kids, like a watch that you can put on your kid's wrist and he can go around play and then you know where he is. You can beep him so you can find him if he gets lost or whatever, or a little drone or something like to hold your keys. And since they don't have any copyright infringement laws over there, you can pretty much just like buy anything from anybody else, like anybody that's selling, take it apart, see what makes it tick, and make your own and make it better. And it's totally legal. You can totally do it. So that what that happened, what that provoked was that people had to be on the top of the game all the time. So you always had to be on the cutting edge. You always had to be looking for new solutions. And those new solutions were in the minds or the products of somebody else. So you knew that the competition could buy you and could take away your great idea for their own. But if the competition actually had a better spin on it, like if somehow they made it so that their design is better and people would buy it because it's better or cheaper, then you're out of luck, even though you came up with it. There's no way you can even prosecute. So what do? You can't sit around and cry. You got to keep innovating and keep going and keep trying to find new solutions. And so it's really cool. Like they make it seem like it's really cool because you can just streamline any project or product. Like there's no like, who am I gotta credit? Who am I gotta? No, it's just like, do it. Just do it. That's also like the problem with China. Like they're just like, they have no brake pedal. It's just power to the metal. Just go all out. But yeah, in that documentary, there's this Swedish guy who's like, oh yeah, I've been in this city for about, I don't know, like 5 years. And he goes like, oh yeah, I'm from Australia or Sweden. I don't remember where he was from. And he says something like, back home, this project we're doing now would probably take us like maybe 2 years, give or take 2 years to do this project we're doing right now. Here, we're almost done and we're 3 months in. Like, whoa, you took a 2 year into 3 month, 5 monther? Like, wow. Like I can see the appeal. But a price for everything, right? But see, that's the one side of the coin. The other side of the coin is that you have Samsung and Apple fighting over like, oh, their charging thing looks like mine. They owe me money and whatnot. All sorts of silliness. It's always the last piece that's a harder one to put in.
This whole thing is hard to put together.
Huh?
It's just hard to put together.
This was hard to put together?
Yeah, I don't know.
Yeah, it's got a trick to it. Like the module is so simple, but then like putting it together, it's like, oh, geez, no, don't fall apart. Yeah, it is kind of hard to put together. But it's satisfying. Hey, no pain, no gain, right? We're all a bunch of sadists. No. I don't know about you.
Masochist, not
Masochists.
sadist.
It is hard to put together. Like you're putting it together and then one thing needs the other thing to come out in order to fit in, but then that takes it apart from where you want it to be. It's like, no. Come on, you. I forget the name of that Chinese city, but it was just a fascinating documentary of that mentality of just like, don't stop, just keep going. But it's sort of admirable, and then you look at all the environmental impact it has and how sad some people get and whatnot. It's like, I don't know if it's that great. A price for everything. So there's a trick you can do where at the end of it, you can put like these two together. No, I don't think I can show you. I'm so concentrated actually on doing it. But see, the thing is, like, there are these flaps that sort of need to go underneath. You guys ever watch that show, the Mr. Something in Peabody? It's like a kid and a dog that travel through time.
Sherman and Peabody.
Sherman and
it's on
Peabody.
Mr. Bolt. It's on Bullwinkle.
Yeah, exactly, yeah. There was also like a Canadian Mountie, what, wasn't there? There you go. Doodly Do Right, that was the name of that other guy. Man, this is harder than I remember it was. All right, so recap. We went through two modulars. The cuboctahedron, I don't know the name of this one. I don't even know who came up with it. I just know it's pretty basic. I've seen it around, several people do it. And yeah. So yeah, I didn't invent this. The Bascetta. But Paolo Bascetta's unit, pretty powerful, looks a lot like the Sonobe. We constructed a nonagon and put in simply the 9-3 to the 9-3 star. Really just opening the possibility of actually constructing the nonagon. So that's also more of that. That's the real focus here. Now it's about exploring and finding more stuff. So good stuff, good stuff. Although something we'll look into next classes and whatnot for combination of other things. And finally, we did an Islamic pattern through overlap. Very simple one. We've done this one before. Probably different than this. Even like this sequence is different from the ones we've done before. But it really just gives the idea that there might be something more to this finding sort of these overlaps. So this isn't the only overlap that we could do. We'll look into more next class. But for now, this is just an example of something that could be done. Another way of using origami to inform our understanding of these designs. And of course, last but not least, the Voronoi diagram, which we put in some points on our piece of paper. We connected them through faults and we described a Voronoi diagrams, which is apparently useful for visual mathematics. So good times. And yeah, we'll leave it at that. Thank you very much for showing up. I'm going to stop recording and we'll keep this going.
I just had a question.